At the agenda for the today's topic. We shall begin our session by introducing time complexity. Then we will discuss the types of time complexity. And then we will discuss all the steps to evaluate the time complexity. Then we will briefly look at the time complexity of various algorithms. Finally, we will sum up what we have learned from this session. So without any further ado, let's get started with the first topic of this session. Introduction to time complexity. The time complexity of an algorithm is the amount of time it takes to run as a function of the length of the input. The length of the input determines how many operations the algorithm will do. It will provide the information about the variance, increase or decrease in execution time as the number of operations in an algorithm increases or decreases. Next up, types of time complexity. We will start with the constant time complexity. Then we will discuss linear, logarithmic, quadratic time complexity. Now let's have a look at them in the detail. First, constant time complexity. When an algorithm is not reliant on the input size n, it is said to have constant time of order big O of 1. The runtime will always be the same regardless of the input. As you can see in the code, every line has the runtime of 1. And they are all independent of any input size, so the runtime is always constant. Next up, linear time complexity. When an algorithm's running time increases linearly with the length of the input, it is said to have linear time complexity. When a function checks all the values in an input data set, it is said to have the time complexity of order of big O of n. As you can see in the code, the loop depends on the size n. So the time complexity rose up to n. Next up, logarithmic time complexity. When an algorithm lowers the input data in each step, then it is said to have the logarithmic time complexity. Binary trees or binary search functions are some of the algorithms with logarithmic time complexity. As you can see in this code, by finding out the mid in every iteration, the runtime will decrease every step, making it approximately logarithmic runtime. Next up, quadratic time complexity. When the execution time of algorithm rises non-linearly up to n square with the length of the input, it is said to have quadratic time complexity. In general, nested loops fall into the quadratic time complexity order, where one loop takes big O of n, and if the function contains the loop inside the loop, then it multiplies. As you can see in this code, because of the nested loops, the time complexity rose to n square. Now that you have the firm grasp of time complexity and its type, we will discuss essential steps to evaluate the time complexity. To understand this, we will take an example of Fibonacci number. This code prints the Fibonacci numbers till n. We will divide this code into 3 parts, isolating all the loops that play a significant role in altering the time complexity. Let's look at the first part. It consists of some independent statement which give constant runtime for each statement. Next, let's move on to our next part, that is for loop. Since this loop runs n times, this will give linear time complexity on n. Next up, the third part, which also has the constant time complexity. Now, let's take a total of runtime, which comes out to be n plus 5. We will then discard the constant part to find the time complexity, which does not affect the overall time complexity. Now, we will have the final time complexity of big O of n.